In this video, we're going to be talking about vectors in 3 dimensions. So we've already talked about vectors in 2 dimensions. We now need to talk about vectors in 3 dimensions. And the reason for this is we live in a 3-dimensional world. While it's great to have a map to get you from one location to another, the topography of the land does affect the travel time. So if you're going over mountains, it's going to take longer. If the land is flat, then it will take less time. So the topography of the land affects the travel time in between. And that, of course, is referring to a 3-dimensional world. So we want to get our vectors into 3 dimensions. When we do this, we're going from a 2-dimensional Cartesian system or rectangular coordinate system into a third one by adding what we'll call the z-axis. Now, the z-axis is going to be perpendicular to both the x and the y-axis. When we normally visualize the z-axis takes the location of the positive y-axis. So the positive z goes straight up in the air. And then where we would normally in a 2-dimensional system have the positive x-axis, we instead have the positive y-axis. So this is z, and this over here is y. So where is the x-axis? Well, the x-axis is coming straight out of the board and hitting you in the face. So the positive x-axis is extending forward. The negative x-axis is going behind the screen. So the negative y-axis would be over there and the negative z-axis would be down. And we often call this a right-hand coordinate system because we can place our right hand into the direction of positive x, which would be straight out of the board, and curl our fingers in the direction of positive y, which is where the positive x in a 2-dimensional system is. And when we do, our thumb points in the direction of the positive z-axis. So in that sense, it is a right-hand coordinate system. We have several learning objectives that we want to cover in this video. We want to describe the 3-dimensional space mathematically so we can do things with it, locate points in space using the coordinates, write the distance formula in 3 dimensions. So it's easier in 2 dimensions. We can always create a right triangle and use the Pythagorean theorem, but how do we find the distance between 2 points out in space? You'll find that it's an extension of the Pythagorean theorem. And then we want to write equations for simple planes and spheres, and we want to perform some vector operations in R3. R3 means real number line for the x-axis, real number line for the y-axis, positive and well, negative, whichever way. That's my right. So the positive out that way and then the negative. And then positive z and negative z. All right. So when we're thinking about that, that makes it 3 real number lines. And so we call it R3, but we write the 3 in the power position. Let's go ahead and take a look now at what it looks like when we draw it in a 2-dimensional system. So it's a 3-dimensional system, but we're actually drawing it as if it were in 2 dimensions. So it looks kind of, well, funky, all right, because it's a 3D thing being drawn on a flat surface. So of course it can't be right. So you'll notice again that we have the positive z-axis coming up, negative z going down, positive y coming over here to the right, and then you've got the negative y coming over to the left. So when you're looking at it, you've got your positive y going off that way and your negative y going off that way. Now it's drawn the x-axis sort of at a diagonal angle as if it were cutting quadrants 1 and 3 in half. It's not. It's coming directly out of the board like this. So it's coming straight towards you and then straight back into the screen. All right. But again, if we talk about this right-hand rule, we can take our fingers and put our fingers in the direction of the positive x and then curl towards positive y, and our thumb points in the positive z direction. And that's what we mean by a right-hand coordinate system or the right-hand rule. Now, if we want to plot points, we need to be able to plot them in a 3D system. So the first method that I'm going to talk about is how to plot them on a regular sheet of paper that's not set up for 3D plotting. And then we'll talk about isometric graph paper, which is set up for 3D plotting, but on a two-dimensional surface. So we're going to start with a three-dimensional point, but written on a two-dimensional flat sheet of paper. It would be a good idea if you have a sticky note with you, and we'll mark off the unit links on one side so that we know how far to move in each direction. So here's our first example. So we want to plot the point 3, -2, 4, right? So that's our point, 3, -2, 4. So the 3 is the x coordinate, the -2 is the y coordinate, and 4 is the z coordinate. So that's what we're plotting. Now, you'll notice that I have an image of a yellow piece of paper here, and this is just like a sticky note. And I've marked off on one side how long the distance is between each unit on that particular graph. So this marks 1 unit, 2 units, 3 units, 4 units. I want to move along the positive x 3 steps in the positive direction, which would be coming out here as if it were in quadrant 3. It's really not. I'm really moving 1, 2, 3 directly out into ahead of the screen. All right, but in a 2D system, we go along here. This point right here is actually the point 3, 0, 0. So this point right here is an interim point, 3, 0, 0. Now that's not what I want to be plotting. I want to be plotting that, but this is an interim point. So I can make a mark there, like maybe an X or something. I used a red dot to help track it. And then we want to move 2 directions in the negative y direction. But we need to put the corner of the sticky note at that interim point. So again, we first moved 3 units in the positive x direction. Then we rotate the sticky note so that the corner is sitting at that interim point, 3, 0, 0. And then it's parallel, this edge is parallel to the y-axis. Now, the positive y direction is off to the right, and the negative y direction is off to the left. And so what we want to do is move 2 to the left in the negative x direction. So we're going over this way, all right, which would be to the left. So when we're looking at this, we're going to go ahead and draw this over. And so we move over 2 spots, and we have another interim point. So this interim point right here in blue is going to be 3, -2, 0, because I've moved 3 in the positive x, -2 in the negative y direction, but I haven't moved in the z direction. Finally, in order to plot the point 3, -2, 4, we need to move 4 units in the positive z direction. So we take off our sticky note, we put the corner at the interim point, and then we move so that this edge is parallel to the z-axis, needs to be parallel. And then we move positive 4 units in this direction. And this final point up here is going to be our point 3, -2, 4. And this is how you would graph it on just regular notebook paper or whatever. Although it's not a great idea because it's very easy to get off. That's why I really recommend the sticky note. So at least you're moving the same direction each time. And you can kind of eyeball whether the edge is parallel to the axis that you're moving along, right? So let's talk about what isometric graph paper is. And to do this part, I'm going to go ahead and share my screen with you so you can see it a little bit closer in. So let me share my screen now. Okay, so you can see here on this isometric graph paper that the lines are not perpendicular to each other like we're used to seeing in two-dimensional Cartesian systems. In a sense, it's trying to represent a 3-dimensional system, but in a 2-dimensional surface. So the z-axis still runs up and down, but they've rotated it a little bit so that the x and the y-axes are kind of coming off. Well, the x-axis is kind of splitting what would have been quadrant 1 and 3, and the y-axis is splitting what would have been quadrant 2 and 4. So it's kind of like we've rotated it and tilted it down a little bit so we can see it. So what we want to do is we want to do the same thing we did before using our ordered triple. So this is called an ordered triple. And so what we're going to do is we're going to start over here with the 3 that we see right here. And we're going to move the 3 along the positive X direction. So we're going to be coming along. So we've got this, and we're going to come along here. So we start at the origin, which is where all of the axes intersect. And we move 1, 2, 3 units. And I'm going to put an X there, make it big enough that you can see it, parallel to the positive X. Now I need to move 2 units parallel to the negative Y. So Y is this one right here that's going from upper left to lower right. So I need to find a line that's parallel to that and move 2 units along it. So that would be this line here. So I move 1, 2, and I'll put a circle right there, make it kind of dark so you can see where it is. It's right there at that spot. And then the last coordinate is 4. So I want to move 4 units in the Z direction. Well, the Z direction is this line right here. So I need to move parallel to that. And parallel to that would be directly on this set of grid marks right here. So I'm going to move up 1, 2, 3, and 4. So that would put it 1, 2, 3, and 4. And that would put my final point right there. So there's another method, of course, of plotting this, and that would be plotting it in what is drawn as a rectangular parallelepiped. In other words, a box, right? A rectangular box. So you can see that in this case, these 4 edges here are all parallel to the positive x-axis. And these 4 lines here are parallel to the y-axis. One of them is along the positive y. And these are all parallel to the z-axis. So you draw a box and then you move the right number of units. But again, I recommend using a sticky note so that you're moving the same distance for 1 unit along all 3. And then this would represent that point out in space. Now let's take a look at the definition of a projection. So when we were drawing and plotting these points, we came up with interim points. For example, after moving along the positive x 3 units and along y to the left 2 units, we plotted an interim point 3, -2, 0. This has a z coordinate of 0, which means that it's actually sitting in the xy plane. If the z coordinate is 0, it's actually in the xy plane, the normal coordinate system we're used to. We call this point the projection of the point 3, -2, 4 onto the xy plane. So it's kind of like shining a flashlight down, where the flashlight is pointing down parallel to the z-axis. And the point in space casts a shadow onto the xy plane, and that shadow is at the point 3, -2, 0. So this idea of projecting is going to come up again and again. You'll see that it's going to come up in what we do with the dot product in the next section. So if we're looking at that, we can also take a point like, say, 3, 0, 4. Notice that the y coordinate is 0. If the y coordinate is 0, then it must be in the xz plane. So this would be the projection of the point 3, -2, 4 onto the xz plane. You may be asking, well, where's the xz plane? If the x goes this way and the z goes this way, the xz plane is the one that comes like this. It's like a sheet of paper coming out like this, or the wall that's coming out of the screen towards you and extending up and down. And we can do the same thing with 0, -2, 4, which would be the projection into the yz plane. Where would the yz be? Well, y goes positive y this way and negative y that way, and z goes up. So the screen itself, this wall, is the yz plane, right? So we haven't moved in the positive x and we haven't moved behind the screen in the negative x. So it's a projection of that point, like a flashlight shined onto that yz plane, where the flashlight is parallel to the x-axis in this case, because it's the x coordinate that's 0. And these projections give us an idea of how to conceptualize the three coordinate planes. Basically, if x is 0, then you must be in the YZ plane because you haven't stepped forward off the screen or behind the screen. So you're on the screen. If y is 0, then you haven't gone to the right or to the left. So you're actually sitting here on this wall, which is the XZ plane. And if Z is 0, you haven't moved up or down, but you might have moved this way or this way. But this floor, if you will, right here, that's the XY plane, the normal XY plane you're used to from before. So now we can describe these as well using the definition that you see here in set notation. So the XY plane is the set of all ordered triples, XY 0, such that X and Y are real numbers. And then the definition of the XZ plane and the YZ plane follow from there. Now, if you want to visualize the planes, I've got a picture here to kind of try to help you visualize. So if you're standing in a corner of a room with your back into the corner and you lay out your right arm, it will be along the XZ plane. And if you put the left arm straight in front of you so that it's perpendicular to the right arm, then this hand is along the YZ plane. And then the floor that you're standing on, that becomes the XY plane. So when you're looking at it, you can tell that this is splitting our three-dimensional space, not into 4 regions like a 2-dimensional coordinate system, but it's actually splitting it into 8. So we have 4 on the top of the floor, and we have 4 on the bottom. And the way that we number these is in the same pathway that we would do before. So if you can visualize looking at this floor, which is kind of this aqua color, here's the positive Y and here's X. So we would call this quadrant 1, that would be 2, then 3, then 4. And then how do you get the ones on the bottom? Well, we just keep going, but underneath 5, 6, 7, and 8. All right. So we number them going again counterclockwise along the XY plane, but above becomes the first 4 and below becomes the second 4. So let's take a look at what this looks like in terms of signs. So when we're looking at the signs of everything, if you're in quadrant 1, you've moved positive X, positive Y, and positive Z. So every coordinate is positive, 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 positive. If you've gone so that you're behind the screen, but you've moved to the right and up, then you have a negative, positive, positive. Behind the screen, X is negative. That would be octant 2. Moving to the next location would be like behind the screen, but in that direction. So my X is negative because I'm behind the screen. My Y is negative because I'm in this direction. But my Z is still positive because I'm still up. And then up here in front of you, again, this time X is positive because I'm in front of the screen, but I've moved to the left, so Y is negative, but I'm still up, so Z is positive. All right, so that positive isn't showing up very well. This is positive, negative, positive. And then coming into quadrant 5, I have moved positive X, positive Y, but I'm down. So my Z value is negative. And then moving behind the screen changes X to negative, but Y is still positive, Z is negative. Moving behind the screen, but in that direction, then both X, where am I? X, Y, and where did I go? Back there. Okay, so my, if I'm behind the screen and I'm below, X should be negative, Y should be negative, and Z should be negative. And coming out here into octant 8, X is positive, Y is negative, and Z is negative. And so you have this last one right here. You can't actually see the one that's in octant 7. It's kind of hidden right now. So that gives us our 8 octants that we have to describe points in 3-dimensional space. Now, the other thing we'd like to be able to do is say how far apart these points are. So to do that, let's go ahead and reconsider how we normally do this in 2 dimensions. And that's with the distance formula, which is really just the Pythagorean theorem. So when you're looking at 2 points in space and you're trying to figure out how far point P is from point Q, and these are on some number system right here, you're looking to see what this is right here, which would be the change in the y values, of course, between P and Q. And this change right here, which would be the change in the x values between P and Q. So you have x1 minus x2 squared, y1 minus y2 squared, because this, of course, is a right triangle, and the distance is the length of the hypotenuse. So the distance formula is really just the Pythagorean theorem in disguise. A squared plus b squared equals c squared, or in this case, b squared. And we can extend this into 3 dimensions. So what happens is we get x1 minus x2 squared, y1 minus y2 squared, z1 minus z2 squared, added together, take the square root. That's the distance. What does that mean in a 3-dimensional world? What does that look like? We've said that in 2 dimensions, the distance is the length of the hypotenuse of the right triangle that connects the 2 points. In 3 dimensions, it turns out that the rectangular parallelepiped or rectangular prism, the box, if you will, that connects the 2 points, the distance between the points is the diagonal of that box from one point as the lower corner through the box diagonally to the opposite upper corner. And that becomes the distance between those 2 points. So it is, in fact, in a sense, the hypotenuse of the triangle that you see here in red, which is also, of course, a right triangle. Okay, so let's go ahead and apply this now. Let's find the distance between these 2 points right here. So again, this is straight line distance. How far is it from one point to the other? So go ahead and compute this now, then turn the video back on and we'll compare our answers to each other. So let's see how you did. So again, remember that because you're squaring them, the order in which you subtract really doesn't matter. You don't even have to be consistent. So I could have said 4 minus 1, which would give me 3 squared, which is the same as -3 squared. I still would have gotten 9. You add these together to get 50, and the square root of 50 is 5 square root to 2. That's how far apart in space those two are, as if you're connecting them with a line, all right? It's the length of the line between those 2 points. So now we want to go ahead and talk a little bit about equations. And the thing to realize is that R3 is not the same thing as R2. In R2, you're in 2-dimensional space. You have 3 possibilities for lines to interact with each other. The 2 lines could be parallel, in which case they never touch and never cross, so they're parallel. Or they could cross, and if they cross one time and one time only. Or they could be the same line, so they cross at all points on the line, but not anywhere off the line. Those are the only possibilities, all right? If the lines are not parallel, then they have to touch only one time. That's the only possibility in 2-dimensional space. But in 3-dimensional space, that's not the case. In 3-dimensional space, we can have 2 planes flying at different altitudes along paths that one is above the other, but the planes don't intersect. So we have 2 lines, they're not parallel, but because one is at a different level than the other, they don't intersect. So we have a lot more possibilities for interactions between lines in 3-dimensional space. Not only that, but the same equation means something different in 1-dimensional, 2-dimensional, and 3-dimensional space. So the equation that you might be used to from 2D, meaning a line, may instead describe a plane in 3-dimensional space and just a point in 1-dimensional space. Let's take a look at the equation x equals 0, which is pretty straightforward. In R1, which is just a single number line, that becomes a point. So x equals 0 represents a point, just 1 point. If we're in R2, which is this one right here, the two-dimensional space, then x equals 0 corresponds to the y-axis, this line where x coordinate is always 0. In three-dimensional space, the same equation, x equals 0, becomes a plane. What plane is it? Well, if x is always 0, but y and z can be anything, then I can go this way, up and down as much as I want. I just can't go forward off the screen or backward behind the screen. So x equals 0 is, of course, the YZ plane, right? So you would see that the same equation is actually representing three different things depending on what coordinate system we're in. And here, of course, are the equations for z equals 0. That would be this one right here. This describes the XY plane, all right? So that's the equation z equals 0. And this is the equation y equals 0. So you haven't gone right or left, but you can come out of the screen or go behind the screen, move up or move down, but you've got to stay on this wall right here, right? Let's now take a look at a more simplified way of describing things. So if we want to take a plane in space and have it be parallel to the XY plane, which most of the time students sort of visualize as the floor, all right? So the floor of the room is the XY plane. If you want something parallel to that, then you simply have to write an equation that z is equal to a constant. So if I say z equal 5, then I'm talking about moving 5 units above the floor, and then I can go anywhere in this flat plane area, like a flat sheet of paper, but I'm at a height of 5 is a way to visualize it. The plane that might be parallel to the xz plane, well, if it's parallel to xz, remember xz runs this way, and normally on the xz plane, y is 0. This would be y equal b. So it might be that y equal 2. So I'm starting here where the origin is, but I'm moving 2 steps this way. And then I'm going to draw it parallel to the xz plane. So that would be the equation y equal 2, and so on. And you can do the same thing for this one and have it be parallel to the yz plane, parallel to the screen, but moved out along the x-axis. Now, a sphere, if we want to write the equation of a sphere, is very similar to the equation for a circle in 2 dimensions. But in 3 dimensions, you could go in any of the 3 dimensions. So your center is going to be the A, B, and C that show up inside the binomial being squared, just like as if it were a circle. And then the constant on the other side is the square of the radius of the sphere. So from the center of the sphere to the edge of the surface. So when we're looking at it, let me grab a sphere really fast. So when we're looking at a sphere, the center of the sphere, of course, is not actually on the sphere. The center of the sphere is right here in the center. And the radius is this distance from the center of the sphere out to the surface of the sphere. A sphere is actually the surface. It's this outer ball or bubble. If you're blowing bubbles, it's the bubble itself, not the space inside of it. So that's the sphere. And the equation looks like this, which again is very similar to the equation for a circle, but in 3 dimensions. So now let's go ahead and figure out how to find the standard equation, the working equation right here, for a sphere with center -2, 4, -5, and containing 4, 4, -1. So what does that mean? That means that the point in the middle of this surface, that's the -2, 4, -5, which are going to be A, B, and C. right? So we're going to have an x minus -2, y minus 4, z minus -5. So what do we not know? We don't know r. So how can we find r? Well, they said it contains this point 4, 4, -1. So 4, 4, -1 is on the outer surface. It's on the surface of the sphere. And this constant over here is the square of the radius, which is the distance from the center to any point on the sphere. So now apply the distance formula between the center and the point on the surface of the sphere, and that will tell you what the radius is. So go ahead and pause the video, work it out, write your equation for the sphere, then turn the video back on and we'll compare our answers. Okay, let's compare our answers and see how you did. So looking at this one, you can see that I went ahead and applied the distance formula. The order doesn't matter that you subtract because you're squaring anyway, but I did, I believe, what did I do? I think I did partly both directions. Anyway, I did 4 minus a -2, which gave me 6 squared or 36. 4 minus 4 is 0, and I don't know why, but on this one I went the other way. -5 minus a -1 is -4 squared is 16, which gave me 52. So the radius is 2 squared to 13, but the formula calls for r squared. So I replaced the a, b, and c with the coordinates of the center, and I replace r squared with the radius squared. Let's talk now about graphing other equations in 3 dimensions. So for example, let's talk about what the line y equal 3x minus 1 would look like in both 2D and in 3D. Now, in 2D, we pretty much know what it would look like, right? This is just going to be the line that crosses the y-axis at -1 and has slope of 3, 2, 3, right, 1. So it is this line that we see right here, right, where this is the y-axis and this is the x-axis. So two-dimensional space, this is what it looks like in R2. And we usually write R2 with a double bar R to represent that, hey, this is the whole set of real numbers twice. What does it look like in 3-dimensional space? Well, in 3-dimensional space, notice the equation doesn't say anything about z. It does not say z is 0. So it does not say that it's in the xy plane. It doesn't say anything about z. If it doesn't say anything, then there are no restrictions on z. So in a sense, you can grab this line and lift it off the page or drive it down into the page. This is describing a plane in 3-dimensional space. So we're going to be using CalcPlot 3D. So let's come over here and I'll click on CalcPlot 3D. This is the home page for CalcPlot 3D. It always looks like this. And I'll put a link for CalcPlot 3D into the lecture notes so that you can see it. So when you're here, this is the home screen. And what we want to do is we want to graph the equation y equals 3x minus 1. So we're going to click here on select. And we just want to graph, oops, I clicked on the wrong one. We just want to graph an implicit surface, all right? So now I could go to one that's solved for y. I could plot that as well, but implicit surface is fine. If I want to turn the original graph off, I just click on the X. Notice that it gives me an option, but that's not the one I want. So I'm just going to take it off. And what I'm going to put in instead is the equation that I'm looking for. So I'm going to put in y equals 3x minus 1. Now you need to get it to execute. So hit enter while you're in the line, and there it is. All right, so we can see what it looks like right here. So we have this equation that became a plane in this space, right? Now, if we're looking at this right here, if we wanted to look at it where it was in the XY plane, we could do something where we have, let me see if I can remember how to do this. Shift Y, function Y, There we go. All right. So now you can see that I'm looking at it from the XY plane. Now you may be saying, well, that doesn't look exactly like a line. It's got a little thickness to it. It does, because CalcPlot 3D is trying to render everything so that it looks three-dimensional to you. All right. And there is an option over here. You can click on this and you can go down to view settings. And on view settings, you can do the view above the XY plane. And then you'll see that one there. You can do the view above different planes. There are also shortcuts, and there will be a guide to help you on learning how to do that. So again, what in 2 dimensions is a line, in 3 dimensions is a plane that extends in all directions forever. Now let's take a look at this equation right here. Notice that this one has both x and z in it, but no y. So in 2-dimensional space, we need to graph in the xz plane. Whenever you're graphing in the xz plane, z always takes the location of the y-axis in 2-dimensional space. So in the xz plane, we're going to have the z-axis coming up this way and the x-axis being the independent. So z is always dependent on x and y. So z always gets to go up, basically. So when we're looking at this, if I asked you, well, what does this look like? If it were a y, what would you tell me it was? You would probably say, well, that's a circle. And the center is at 0, 2, and the radius is 4, because r squared is 16. So the circle is going to be centered at 0, 2. So that's 0 in the x direction and 2 in the z direction. So right there, and notice it's not on the shape, but it's a part of how to draw the shape. So I put a C for center, and then I can go 4 units, 1, 2, 3, 4. I like to go 5. 1, 2, 3, 4, 5. I make my 5s longer. 2, 3, 4, 5. 1, 2, 3, 4, 5, running out of space. So I need to go up 1 more. So I've got a spot there. 4 to the left, 4 to the right, and 4 down would put me at -2. And I can't draw. So actually, that's not too bad for me. All right, that's about as good as I can do. All right, so what is this going to look like in 3 dimensions? So think for a moment. It doesn't mention y. It does not say y is 0. It just doesn't mention it at all. And since it doesn't mention it at all, it can be anything. So grab hold of this circle and lift it. Now, where is the y-axis? If that's z and that's x, where's y? Positive y is actually into the board, and negative y is coming out and hitting you in the face, all right? Because y would be counterclockwise to x. So positive y is actually into the board. So the y is coming in and out of the board in this particular view. Grab the circle and pull it along the y. So it's going to make a tube or a right circular cylinder. So let's take a look at what this one looks like in 3-dimensional space. So coming over here, I can leave that on, but I can just turn it off. And now I'm going to do an implicit surface again. And I want, what do I want? X squared plus z minus 2 squared equals 16. So I have x squared. I do not have a y squared, so I'm going to take that out. Right? And my z squared is positive, so make sure you change that. And my z is going to be z minus 2 quantity squared, and it equals 16. So make sure you get it typed in correctly. And notice that right here, this isn't going to be good enough, all right, because it's only graphing between -2 and 2 for all of these. And I want it to be a little different. So I want it to go back to the normal view of z being up. So I'm going to hit the home screen, which on your computer may also be the function left arrow. Well, it's not working. Try that. Well, Pipple. Oh, I'm not clicked in it. There we go, in the home screen. Now, notice it didn't turn on because I didn't hit enter. So I can hit enter, or you could hit graph. And I'm only getting this, which this doesn't look what I was expecting. I was expecting a tube. It's because it's only graphing between -2 and 2. So come up here and hit the magnifying glass with the minus sign so you can come out. And then you'll see that in effect, you are getting a tube and that it is centered here. If I rotate this around a little bit, it is centered there on the XZ plane at 0, 2. And it is basically a circular cylinder, all right? We're actually going to call this a prism, all right? Because it is the same shape all the way along. All the cross sections are the same, but we'll get into that later on. So same equation, but two fundamentally different things. In 2D, it's a circle, and in 3D, it's a tube, all right, or a circular prism. All right, now can you graph a circle in 3D? Well, of course you can, because you do it all the time, right? You know you've got to be able to do it. So how can you get just the circle without getting the whole tube? You have to specify that third coordinate. So for example, if we wanted to do our last one, we could specify that the Z value is 2. So that would take that circle, or specify the Y value is 2, and take the circle and put it at y = 2. In this case, we have a circle, x squared plus y squared equals 4. So in 2 dimensions, it's coming around, centered at the origin, with radius of 2. But this says it's at height 5. Okay, so occurring at the level z = 5. So if you want to get a 2-dimensional shape in 3 dimensions, one of the things you need to do is specify all 3 dimensions. So it is possible. Now let's go ahead and work with our vectors here in R3. So we're going to use the same notation that we did for R2 when we did the 2-dimensional case. We're going to use angle brackets to represent a vector, all right? And remember that if it's typed and it's boldface, it's a vector, not a scalar. So this is vector v, which is x, y, z. So it's just an extension of the 2-dimensional case. Our origin is now 0, 0, 0, the ordered triple. And our vector in standard position is going to have initial point at the origin and the terminal point, wherever it stops in 3-dimensional space, be x, y, z. The 0 vector, of course, is 0, 0, 0. We can extend the standard basis vectors, I and j, and we'll have another one now called k, which goes along with z. So I now becomes 1, 0, 0. So it's a 1-unit long vector pointing in the positive x direction. And j is 0, 1, 0, which is a 1-unit long vector pointing in the positive y. And k is 0, 0, 1, 1-unit vector pointing in positive z. These are often written with hats on them. So when you're handwriting it, for example, you might write I hat, j hat, and k hat. And in physics, that's typically the way they're referred to. And we call it a hat, even though it's a caret symbol. But I don't know, it just rolls off the tongue, right? I hat, j hat, k hat. So when we handwrite it, this is our way of indicating that it is both a vector and the standard basis vectors. So it's the 1-unit vector in each of the directions of the axes. Now, this means that any vector that we have can also be written in terms of I, j, and k. So we can write xi plus yj plus zk, which would represent the same vector as x, y, and z. Let's take a look now at some of our 3D vector examples. So let's start with this one. We want to express ST in component form and in standard unit form. So that's in terms of I, j, and k. So ST has to start at S and end at T. So remember that the arrow is going in the direction that it's pointing. So the initial point is S. the terminal point is t. Then we take the terminal point minus the initial point. So we're going to have 213 minus 382. So our vector ST is going to be 2 minus 3, -1 minus 8, and 3 minus 2. And if we simplify this, we get the vector -1, -9, 1, right? And once we have that, we can put it in terms of the standard unit vectors, also called the standard basis vectors, I, j, and k. So this is the same as -1i or -i hat minus 9j hat plus k hat, right? Let's take a look at more. We just have a little bit left to cover, which is again the properties of vectors in space. Now we looked at the properties in two-dimensional space, and you'll see that they're really just extensions of those into three-dimensional space. So we let a vector v be given by a, b, c, and a vector w be given by x, y, z. Now this presumes that they're in standard position, so the origin is their initial point, their terminal points are a, b, c, x, y, z, those ordered triples. We're going to let k be a scalar. Now, a scalar just means any real number. 5, -2, 1/3, pi, e, square root of 11, whatever. A real number. If I want to multiply a vector by a scalar, I just multiply each component by that real number, and that will give me scalar multiplication. To add or subtract vectors, I add or subtract the corresponding components in the same position. So to add, I would take the 2 in position 1 and add them together to become the position 1 in the new vector v plus w. And if I'm doing subtraction, the order does matter. You want to make sure that you do the first one, which is the positive one, minus the second one. So a minus x, b minus y, c minus z. Now, again, vector magnitude, since we're assuming that these are in standard position with their initial point at the origin, remember our extension of the Pythagorean theorem, the distance formula, would have been x1 minus x2, y1 minus y2, z1 minus z2, each squared and added together, take the square root. In this case, the initial point is 0, 0, 0. So this is a minus 0 squared, or just a squared, b minus 0 squared, or just b squared, and c minus 0 squared, or just c squared. So if for a vector that's in standard position, the magnitude, the length of the vector, not the direction it's pointing, but the length of it, literally like tape measure, how long is it, can be given by the square root of the squares, the sum of the squares of the individual components. Now, if you want to find a unit vector in the direction of a vector, you simply take the vector and divide by its magnitude. So in this case, you take each individual component and divide by that length of the vector. So we have one last example to do, and this is going to be the vector v, which is -1, -1, 1, and the vector w, which is 2, 0, 1. We want to find a unit vector in the direction of 5v plus 3w. So not a unit vector in the direction of either one of these, but a unit vector in the direction of a combination of these. So we're multiplying each vector by a scalar in scalar multiplication first, then adding the vectors together. That will give us the vector 5v plus 3w. Then we have to find its magnitude using the formula that you see here. Once we have the magnitude, to get the unit vector in the same direction as 5v plus 3w, we divide each component of the vector by its magnitude. Go ahead and pause the video, then work it out and turn the video back on so we can compare and see how you do. Okay, so it's time to see how you did. This is our last example, so hopefully it went well for you. When we're looking at this, again, the first thing we're doing is scalar multiplication 5 times vector v plus 3 times vector W. So multiply the 5 by V first, the 3 by W. Once you've done that, add the two vectors together by adding corresponding components. So the -5 plus 6 gives me 1. The -5 plus 0 gives me -5. And 5 plus 3 gives me 8. That is the vector 5V plus 3W. Now, I don't know how long it is yet, but I want a vector that's only 1 unit long, but points in that direction. So what I need to do is find the magnitude of it by applying the formula. So I take each component, square it, add them together, and then take the square root, which gives me 3 square roots of 10. To get the unit vector in the same direction as this vector, but only 1 unit long, I take each component and divide by the magnitude. And that gives me the unit vector in that direction. So I hope you've learned something from this video, and I hope you'll join me for the next video where we'll be talking about dot products, and we'll be using CalcPlot 3D more often. As you'll see in the days to come, we use CalcPlot 3D quite a bit. I hope you'll join me for the next video.